All right, I'm here with Vlatko Vedral. Vlatko, thanks for joining me.
My pleasure. Thanks a lot.
So one of the great outstanding problems in physics is that quantum mechanics and general relativity have not yet been reconciled. Before we get into the experimental work that you've been developing, what are some of the candidate theories that aim to unify quantum mechanics and general relativity, and why are they so challenging to probe experimentally?
Yes, there are basically, in a way, three main directions to unify quantum mechanics and general relativity. You can think of people who just approach it in a standard way. We need to quantize gravity. So basically, we are taking quantum mechanics as it is and simply applying it as we apply it to other forces like electromagnetism. So we say the same way we quantized electromagnetism, we can really quantize gravity as well. And this would be some kind of quantum field theory approach to gravity. So even within this direction, you will probably find a number of different approaches how to do this. So that would be one direction. So impose quantum mechanics on gravity. The other one would maybe be to go the other way, to say, can we make quantum mechanics a bit more geometrical? So this would be geometrization of quantum mechanics. Phrase quantum mechanics in a way that resembles as closely as possible gravity, which is all about geometry and curvature of geometry and so on. And then try to unify the two. So those will be people who believe that somehow quantum will have to conform to gravity rather than the other way around. And then there is a third road which says, well, probably the new theory will be something that goes beyond both of these theories. And you know, something that you frequently read about string theory is possibly this approach which says, well, I think we can construct a theory which is above both quantum and general relativity. And both quantum and general relativity are just special limits of this new theory. If you take one limit, you will get quantum mechanics. If you take another limit, you will get gravity. And somehow string theory claims to unify both of them. So I think these will be three very, very broad approaches. And you know, within them, you have many little roads, basically.
And what makes these candidate classes of theories so difficult to test experimentally?
Extremely difficult, because I think they all should, if they're genuine quantum gravity theories, they should really all agree at the lowest level of approximation. So if you take the approximation where the gravitational fields are very weak, so you know, if you're thinking about Earth's gravitational field, instead of being very close to a massive black hole, so if you think about a weak, almost what people call Newtonian limit of gravity, very weak gravity, then basically all of these three approaches that I outlined should in fact agree with one another. But even this low level of approximation is extremely challenging for our experiments. So even this first step where they would agree, I think it's hardly accessible to us experimentally. And the key issue is really maintaining a superposition, a quantum superposition of an object that's large enough to be affected gravitationally as well. So you really want to be in a regime where both of these matter, both quantum mechanics and general relativity, and it's very hard. And on top of it, like I said, it's quite depressing, it seems to me, that all of these three approaches would even agree at that level. So probably to discriminate them, we need to go one level up, which is even harder, I think.
So constructor theory offers a radical new way to experimentally rule out some of these candidate post-quantum, post-relativity theories. Now, before we get into your work on this, let's set the stage a little bit.
Yes.
What's the difference between dynamical laws of physics, like the laws of general relativity and quantum mechanics, and the principles of constructor theory?
Yes, this is a very, very interesting question, actually, that I find fascinating, because dynamical laws is the way we usually phrase, as you said, all of physics, in fact, not even just GR and quantum mechanics, but of course, these are the two most fundamental theories, if you like, and everything else follows. So the way we phrase this is that we give the initial state of the system, whatever this is, And then we use the dynamical equations of motion to calculate the future states of your system. And then you simply derive your experimental predictions from this future state, and then you test that against your experiments. And I think most of physics can be basically summarized in this way. And you know, this approach goes back to certainly Galileo and Newton, who had this vision that you should be able to describe regularities in nature in this precise way. Now, principles is something probably that people like Einstein emphasized a lot. You know, Einstein said, well, look, in addition to dynamical laws, what we do have is symmetries in nature. So it's clear that, you know, for instance, if I look at the universe from a different perspective, if I rotate myself and look at a different portion of the sky, then we pretty much notice similarities between the previous view. And so this is something that we call rotational symmetry, that the universe should be more or less the same in its global features wherever we look. And Einstein, of course, discovered first the theory of special relativity, which is yet another symmetry. It says, you know, if someone is moving at a certain speed with respect to you, all the laws of physics should be identical. And this is not a dynamical law. You know, it's not something where you can say, oh, how do I compute with this now? You know, what's the initial state and so on. This just says whatever you are doing in your physics has to be symmetric with respect to all of the observers that are involved. Yet another principle, by the way, which also follows from symmetries is really conservation laws, right? Conservation of energy, conservation of momentum, and so on. And so now the question is, what exactly is the relationship between these two? And I think at the moment, the way we do physics at present is really to impose these principles on top of our dynamics. So, you know, you come up with some kind of dynamical law and then you say, oh, but does this obey energy conservation? And then you realize, oh, it doesn't, you know, okay, maybe I have to tweak it a bit to include energy conservation. I'm caricaturing a bit, but that's roughly how it works. But the fascinating idea, I think, here, and that's something that David Deutsch, I think, proposed a while back, and then Chiara Malletto took very seriously and developed much further. The idea is, could everything really follow, as it were, from a basic set of principles? Do we really need this kind of halfway house where you talk a little bit about dynamics, a little bit about principles, and then somehow you try to fit them together? Could it be really that everything follows from basic principles? You know, if only we had access, if only we understood what the fundamental principles are, the rest of physics would follow. And I think this is a fascinating idea.
Right. So given this difference between principles and dynamical laws, with the former being kind of higher level and dynamical
Yes.
laws being closer to the physical systems that you're
Yes.
looking at or studying, how could these principles help us to uncover new dynamical laws, like any that might supersede those of general relativity or quantum mechanics?
It's a great question, actually, and that's exactly where these principles come in, because they act as constraints on what you can do. So let me give you a very simple example of this. You might be thinking that the basic equation in quantum mechanics, the Schrödinger equation, is, let's say, to be modified. And your motivation could be anything. You could be thinking, well, you know, things cannot be superposed beyond certain limits. So let me include that into the Schrödinger equation, because Schrödinger equation would suggest to us that anything can be superposed in principle. It's just a question of money, you know, it's a question of technology, whether we're able to do that. But some people believe maybe there is a limit to that. And now you may say, let me tweak the Schrödinger equation a little bit and add some extra terms to it. And when you do that, now you're in a good position to apply various principles to this and say, wait a second, this new theory that I'm proposing, and various collapse theories, I'm saying this because various collapse theories that are motivated by gravity come into play here. If you do that, you're going to, does this theory now obey things like energy conservation? Would that still be true in a new theory? And actually, whenever you tweak quantum mechanics in some way like this, you will realize that it seems to violate one of these principles that we think are very fundamental. So energy conservation is certainly there. Another one that's been very important for Chiara and myself in our work is the principle of locality, of course. And this clearly underpins quantum mechanics. All of our quantum field theories are local in this sense, which simply says, you know, that the point at which you act in any way you care to choose to act is the only point really in space that should be affected. And you should not be able to affect things at a distance. And if you change your dynamical laws sometimes, you will realize that actually you might be violating this principle of locality. So we have a set of these principles that we think are fundamental, as you say, maybe more fundamental even than the dynamical laws. And so anything we build on top should really conform to these basic principles. Now, you know, do we have enough principles to really nail down a single theory? That's really maybe the most exciting open questions, because I think the principles we are working with are still satisfied by many different theories that we can think of.
So in your research into studying how systems in which there are quantum mechanical features and gravity, how these systems must behave, what other constructor theoretic principles have you been applying, and how have they been fruitful to your research?
I think the most beautiful somehow avenue there is really to use principles of information theory. And that's really proved to be very fruitful there. Because what you are really saying, and you're trying to kind of distill the essence of classical and quantum physics in some sense. And because gravity is still fully classical, you are thinking what kind of laws of information theory would follow from this kind of behavior. And quantum mechanics, of course, leads to a completely different type of information processing. And, you know, our new technologies, quantum information technologies and quantum computation basically are all built on these kind of ideas. So the question here, you can phrase it in a very simple way. If I have a system that obeys one set of information theoretic principles, and I couple it to another system that obeys a different set of information theoretic principles, what happens to the joint system? So this is something that we call hybrid systems. And it's distilled exactly from this question. If I have a quantum system, let's say in a superposition, and I have gravity, and I put them together, what happens? And what Chiara and I realized is that we can ask this question at a much, much higher level. We can really say, if you have a system that's capable of certain kind of information processing and another system with different laws of information processing, what really happens when you put these two systems together? And actually, with very few assumptions, you will realize frequently that you get into a contradiction with these basic principles, and you will conclude that you cannot have these kind of hybrid systems. Either both systems must conform to, so to speak, to the quantum type of information processing or to the classical, but if they are hybrid, they are going to lead to some kind of contradiction, which is very interesting. Either, you know, violation of energy conservation or the locality principle or things like that.
So I wonder if you could give a few examples of constructor theoretic principles that you've been applying that aren't sort of already known, such as the principle of conservation of energy. What I mean is, what are the constructor theoretic principles of information that prior to constructor theory would not have been obvious and that you've been using in your research?
I think the most important thing is really this issue of copyability. And why is this important to a physicist? Because every measurement can be thought of. You know, every measurement, of course, is a kind of an interaction between one physical system that you call an apparatus, a measurement apparatus, and another system that you are investigating. So you can always elevate this to this higher level where it's really two physical systems interacting with one another. But if you look at what a measurement should constitute, then it really is copying of a certain kind of information from the system onto the states of the apparatus. So the minimum requirement there to be able to make a measurement is really this kind of copyability. For every state of my system, can I create a distinguishable state inside the apparatus that mirrors the state of the system? And this is something, you know, in the jargon of computer science, this would be like a controlled NOT operation. So I want to be able to perform a controlled NOT gate between the system and the apparatus, which actually takes a state of the system and copies it into the apparatus. And now what's interesting in quantum mechanics, and this is something that David Deutsch and Chiara Malletto would call a super information medium, is that actually quantum mechanics gives you more in the sense that you are not just copying one type of property, but you can copy many, in fact, continuously, infinitely many, if you like, types of properties. Which confusingly enough, if you don't think about it, you will get actually confused about it, seems to lead to the violation of this copyability. So there is no universal copyability in quantum mechanics, which is exactly what underpins the measurement problem for us. So namely, what this means is that you can have different states of quantum systems that cannot be distinguished with perfect 100% efficiency. So you can copy one set of states, you can copy another set of states, but when you put them together, they give you something more than copyability. They are not subject to this kind of classical logic of measurement. And I think this was the key property for us, because what we end up taking ultimately is a classical system which can be copied. We take another system which you can think of as a quantum system, but it's even more general than that, if you like, which cannot be copied. And then we put them together through some kind of interaction, and we ask what happens now. And I think this was the key principle in all our work so far.